1. We rearrange a little bit more and we finally see why we did all those calculations. M plus E times 2 to the 23 appears. That's our bit representation. Chosen freely. Again, with mu equal to 0, this approximation is correct at 0 and 1. But it turns out that setting mu to this number gives the smallest error on average for numbers between 0 and 1. So going back to our formula, we apply our trick, as m divided by 2 to the 23 is indeed a value between 0 and 1. We rearrange a little bit more and we finally see why we did all those calculations. M plus E times 2 to the 23.
So basically started off with this.
So the creators here, we take the logarithm base. The trick log of 0 is indeed a value. We finally see 23 appears. That's our
okay, this isn't giving exactly what I thought. Okay, I guess we got to go back to. Let me just make sure this doesn't pop up anywhere else. Yeah, I don't think it will.
Own logarithm.
Oh, I guess he does show it. It's right here. Like this is literally the bit. It's like literally just like this and this right here. They're just flipped. Like this is 2 to the 23 and this is 2 to the 23. And like m's to the right and m's to the left here. So this is what we have. So basically log of this. Wait, we actually started with the number itself. We didn't do like log of 2 to the 23 times E plus M. We did log of this thing over here. So we did log of basically like the real number version of it. And that gave us like the bit representation. It's kind of crazy. Yeah, it basically gave us like the bit representation. Basically gave us like a function of the bit representation. It's like the bit representation times like 1 over 2 to the 23. So it's the bit representation shifted over by 23. Is this 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14. Okay, so we chop off this. So it's basically just the exponent part is left. So it's basically equal to like the exponent plus mu minus 127. It's approximately equal to, the log is approximately equal to. Interesting. So we have float of y. And so we have y as a float. And then we say log of y. And that's approximately equal to, I don't know, the bit version of y, extract the exponent, add mu, and subtract 127. The exponent part. How does the exponent work with like the minus 127? If we wanted to do like 2 to the 2, would it just be 2? Would it just be 2 like that? What happens when we subtract 127 from that? We get kind of like a negative number version of binary? Or did we have to take our exponent and shift it up 127? No, we need to subtract 127. I don't know how it kind of gets negative though. I don't know how that kind of works.
Are completely different. But with 23 bits, we can represent numbers from 0 to, but not including, 2 to the 23. Again, that's not exactly what we need. For scientific notation, we need the mantissa to go from 1 to 10, or in binary scientific notation, to go from 1 to 2. So the number is negative, but the number is Quake 3. That means 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and so on. With 8 bits, we can represent numbers between 0 and 255. But that's not exactly what we need. We also want negative exponents. This is why everything is actually shifted down by 127. So instead of 2 to the 4, we actually have 2 to the 4 minus 127. If we actually want the exponent to be 4, the bits need to be set to 131. Because 131 minus 127 is 4. The last 23 bits.
Yeah, I guess I'm not sure what happens then when you do, if you just had like the,
Are the mantissa.
If you just had the decimal representation of 4, then you do this minus 127. I don't quite know how to do this operation, but internally it's got to do like 2 to the negative, 123 or whatever. It's just representing this as that. And then you have to do your operations in this space to get a new float. I guess maybe like the CPU has support for floating point operations.
in computer science, this correction term can be chosen freely. Again, with me, why we did all those calculations.
So I guess when you're looking at an IEEE number, you can't just read off the exponent like, oh, this is 2 to the 100 and whatever. You actually have, you actually do have to subtract this by 127, and like that's the exponent. And like this is the 1 point whatever like representation. Yeah. How do you get the actual like exponent? You subtract this by 127. And how do you get the actual mantissa? You just do 1 dot and then in front of it. That's it. That's the number.
M perf. Armed with this knowledge, we can finally start with the 3 steps of the fast inverse square root.
Just recall that the log of this thing is actually equal to basically, it's like approximately equal to the exponent part of y plus mu minus 127. That's probably this right here. This yeah, this right here is probably mu minus 127, this value here. I don't know why he's just shifting it over by 1. I guess we'll find out in a minute.
The intuition behind the second step is the following. Remind yourself, bit shifting a number to the left doubles it, and shifting it to the right halves it. But what would happen if we did something like this to an exponent? Doubling an exponent squares the number, and halving the exponent gives us the square root. But now also negating the exponent gives us 1 divided by square root of x. That's exactly what we need.
So, like our goal was like compute 1 over the square root of y. But our goal equivalently is just to do y to the negative 1/2 power. That's it. Okay.
So let's remind ourselves what our goal is here. We have our numbers stored into y, and our goal was to calculate 1 divided by square root of y. As I've already said, calculating this directly is too hard and too expensive. But we've extracted the bits from y, and we've seen with the IEEE standard 754 that the bits of a number are in some sense its own logarithm. That means in I, we have stored log of y, up to some scaling and shifting. I claim that our problem becomes way easier if we work with logs. Instead of trying so hard to calculate 1 divided by square root of y, we instead calculate log of 1 divided by square root of y.
All right, let's just think. So let's say we actually want 1 over the square root of y, but so like this is easy to compute. So like what if we just say, all right, this is easy to compute, log of 1 over square root of y. If you gave me this, then I would just be like, all right, if you gave me this, I'll just raise like 2 to that power, and then that just equals 1 over the square root of y. So if that's what he's going for, like he'll say, okay, it's easy to compute this thing, then how could you use this thing to compute what we actually want? You would just raise 2 to this thing. If this thing equals x, then just do 2 to the x. It's kind of weird if this is like a decimal number, though. Like that's going to be weird. Maybe that doesn't work as well.
We rewrite this to log of y to the power of minus a half, so we can take out the exponent. Calculating this is stupidly easy. You might think, oh no, we have a division in there. Didn't you say in the beginning that divisions are slow? Well, yes, but remember that we can do bit shifts now. Instead of dividing by 2, we just bit shift once to the right. This already explains why we do minus I bit shifted once to the right. But why is this number 0x5f37590f here again? Well, because our logarithm is actually scaled and shifted. So let's calculate and
I like how he did 9df. It's like 90f.
Well, because our logarithm is actually scaled and shifted. So let's calculate and understand where it comes from. Let gamma be our solution. Then we know that log of gamma equals to log of y to the power minus a half, which equals to minus a half times log of y. Now, solution. Calculate and understand where it comes from. Let gamma be our solution. Then we know that log of gamma equals to log of y to the power minus a half, which equals to minus a half times log of y. Now we replace the logarithm with the bit representation. And then we just solve for the bits of gamma. I'll spare us the details, but this is the result. The magic number turns out to be the remnants of the error term mu, the scaling factor, and the shifting. Now we have the bits of our solution, and we can just reverse the steps from the evil bit.
Yeah, I guess that's different from what I thought was going to happen. Like, we didn't take log of gamma and then say, all right, let's do 2 to that thing. We basically did this substitution here.
And then we just solve for the bits of gamma. I'll spare us the details, but this is the result. All for the bits of gamma.
Basically, just did this substitution. Yeah, I kind of thought that we would go straight to computing like a number. It would be like, this is like 2.13246 or something, and then we would have to like work with this. But we actually are still in like math space or like algebraic space where we just said, all right, let's just take the log of this because we know we have this mathematical expansion for log, which we can kind of expand. You kind of like expand this thing, and somewhere in this expression, you basically have like gamma kind of, the log kind of goes away, and you have gamma, and through some algebra you can like subtract, this stuff, and you can like subtract this, and this goes away, and you get gamma is equal to this mess over here. It's kind of weird too, because the ultimate thing, it said we solve for the bits of gamma. It's almost like we say, all right, set like gamma is equal to 0 0 0 0, like 32 zeros, and then we basically solve for like the mantissa of gamma is equal to something. We get the exponent of gamma is equal to something, and I guess like this, the sine of gamma, is also equal to something, and then we just basically set those bits. This is like the exponent of gamma, and then this is like the mantissa gamma. So if you have gamma is equal to this, then you know that gamma is equal to the representation of it on the computer is equal to,
which equals to -1/2 times log of y. Now we replace the logarithm with the bit representation. And then we just solve for the bits of gamma. I'll spare us the details, but this is the result.
So you're not explicitly solving for the bits. You're actually like, this is in kind of like numeric space. This is in kind of like long space. So you say that gamma is equal to this thing. Yeah. Even though these are the bits of gamma. So it's almost like so gamma is equal to 1 over square root of y. We take the log of both sides. And then and you eventually get kind of like lambda is equal to something, but you don't even get lambda is equal to something. You get the mantissa of lambda plus, this. This is so weird because this is like crossing like the bit representation with like the real number representation. Like this is very weird. I don't know if okay, I guess you do compute this actual number here, and like this expression is a float, and you kind of like this is a number, and so then you take that float and you just save it into another float, or like you just keep the float or whatever. Yeah, it's so weird. Okay. So you do compute this float, and then you just like, those are the bits. Oh well. Till next time.